Well, this time, welcome back, everyone. This will be our final class meeting. So congratulations on getting through all this course material. Even though it's 8 weeks, it's been a busy 8 weeks. Feels like we've been through a lot. And by the way, if you are taking Calculus 2 in the fall semester coming up, probably good sections to review before beginning the fall semester would be any differentiation property in Chapter 3, and specifically in Chapter 5, Sections 5.3, 5.4, 5.5 on integration. Reviewing and refreshing that information will be really helpful for starting off Calculus 2 because it's one of those classes that pretty much just hits the ground running starting in Chapter 7. But for our purposes today, we'll be reviewing the final exam, so we'll be looking into some of that same content just mentioned. We're on the example number 6, and we're pretty much just going to do as many problems as we can with our remaining time. I might skip around here and there a little bit more just so we can get to certain problems before we run out of class time. But like we mentioned before, if you have other questions you would like to see done on that document or anywhere else in the course, don't hesitate to interject at any point, and I'll be happy to look into your questions first. Well, speaking of which, the final exam, the official day is Thursday, so we won't hold class on that day. It's open to be scheduled on Friday as well, which makes grading a little bit tricky since usually if an exam is taken on Friday, it's kind of a unknown when the exams get sent back to me. Sometimes they get sent back quite late on Friday. So my opportunity to grade final exams really is going to start in earnest on Saturday once I have the full set. So I'll be doing a lot of other grading, so take advantage of the extra credit opportunity, particularly on any late homework assignment. I'm really going to start there for grading, get completely caught up on homework, then switch over to grading the final exams. Final grades are due on Tuesday of next week, but I don't like to grade on the final day because internet goes wrong, then I've got a big problem. So I'm going to try to make sure it's complete on Monday sometime at the very latest. But that's pretty much the wrap up for the announcements for the day. Any questions or comments at all before we get started, or any problems we'd like to start with? Okay, let's begin. We're reviewing differentiation, chapter 3, on the example number 6. So we've done some tricky derivatives already, some chain rule work, product rule, quotient rule. And here's another set of problems just with the same kind of theme. So on part D, we reviewed a couple formulas before ending class. The formula for differentiating and integrating a general exponential. Here we're doing a differentiation with the product rule. So first factor is 2x, second factor is sine inverse x. Product rule on this one. So really that's two tricky differentiation formulas that we have to deal with. First, for 2 power of x, we can say y prime by our formula we have on the right is going to be differentiate 2 power of x for 2 to the power of x times natural log 2. Then copy sine inverse x. Go plus, copy 2 to the power of x. Differentiate sine inverse x. Here we need to be really cautious. When it says sine inverse x, we don't mean 1 over sine x. That power is not an actual power. It's denoting an inverse function. And so we have a new derivative, well, not a new one, but a new idea here. When we're differentiating the inverse function, we're going to go times 1 over the square root of x squared minus 1. So that derivative is tricky to recall. This one came from section 3.6. That's a good one to have memorized, ready to go on your page of notes allowed on the exam as well. There's several derivatives. All 6 trigonometric functions can be inverted on the right domain. So watch out for these wherever they occur, whether in the form of differentiation or in the form of taking an antiderivative. For example, if this comes up, antiderivative of 1 over 1 plus x squared, then this one is also quite tricky. This is another inverse function, still section 3.6. that would be tangent inverse of x plus a constant as an antiderivative. But that's the first one down for the day. Any questions at all, folks, getting through the product rule? Okay, well, we're on our way with this one. We're less than 6 minutes in, one down already. When we're looking at here, this one's going to involve the chain rule. So in the chain rule setup, I think we usually color coded it this way. Green will be the inner function. Blue is going to be the outer function. We differentiate the outer function first to get started. The arctan is just a different way to say tangent inverse. And this formula really plays two roles. It's an antiderivative formula, and it's a differentiation formula at the same time. Differentiate this answer, and you get the integrand, 1 over 1 plus x squared. So likewise over here, differentiate arctan, and we can say y prime is going to be 1 over 1 plus whatever your input is to power 2. Through the chain rule, chain on the new derivative, multiply it by the derivative of something. The something is the inner function, hyperbolic tangent at x. So tangent hx goes here and here. And now we just need to take the final derivative. If this is ordinary tangent x, its derivative is secant squared at x. And same with the hyperbolic. Derivative of hyperbolic tangent x is hyperbolic secant squared x. So the whole problem ends as soon as we write 1 over 1 plus tangent h squared at x, or you can leave it in that notation there with the parentheses if you prefer. We're multiplying, so I'll throw the numerator or the derivative into the numerator as we multiply by secant h squared at x. And I actually want that to be green to show that's the derivative of the inner function. That stage we stop. We don't have to convert this to the base e exponential. We can just leave it to write in that format. So that's as far as that one goes. Any questions on getting through the chain rule there? Okay. And last class, pretty close to the end, we made a pretty big deal out of the fundamental theorem of calculus parts 2 coming up. And this is the problem where it really actually does come up. So let's pull that down from up top here on the notes where we cited it. We'll use it here to differentiate part g. Excuse me, this is part f, the function is g. It's got quite a lot going on with it because in the position of where we expect to see just x, we actually have an x squared that we're working on. That makes this one a chain rule problem as well. So we'll hit this with chain rule. Inner function is x squared. Kind of hard to highlight the rest of it, but I'll do the best I can. The outer function is all of the rest of that. So the review of this says, if this is your function, g of x integrates from any number a that's in the domain of the function f, the integrand, to variable x, then differentiate that integral function, and you just get the actual integrand itself. Swap the variable to x, and that's the whole answer. This one has a little bit more going on. We saw this happen in the homework and in the notes for section 5.3. Chain rule, whenever this gets involved, turns the problem into this. G prime at x is going to be equal to, we differentiate the integral function, we get the integrand. So let's take the integrand, we're swapping to variable x, but really we're just going to leave a placeholder here, go something squared times e to the power something, then we chain on a new derivative. If it was just x right here, x would have gone into these positions, both here and here. Derivative of x is 1, so that would have been irrelevant. And that's what this theorem is saying. Just swap from variable x, t, we see here, to the variable x. And we're running through the theorem. If you put in x squared instead, we will go into these positions, x squared, but this is where the chain rule gets involved. We differentiate that x squared to get a 2x. So g prime of x is now at this next stage, x to the power 4, e to the x squared times derivative of x squared is a 2x. That means it simplifies even further. We can combine our like bases and say this is 2 x power 5 times e to the power x squared. So this function was complicated. It's through the fundamental theorem part 1, but a chain rule all at once. Any questions on getting through this one? Okay, well, I think that wraps up the example 6, a quick tour of differentiation properties. We'll still differentiate stuff. Example 7 looks like it's just more differentiation. Let's go on to this next one. So we have f at theta is 3 tangent theta. We want to evaluate second derivative at 0. A process for a problem like this one is first take the first derivative, f prime at theta. Once we have the first derivative, we can now differentiate it, get the second derivative here. And once we have that, we'll just evaluate it at 0. So back to this function, if we differentiate tangent theta, we get secant squared theta. So this just turns into 3 secant squared theta with the constant multiple rule. That's the end result on this one. So far so good. Now we just move on to second derivative, f double prime at theta. Here it gets a little bit trickier because at this stage, it's a chain rule again. Let's rewrite this. It's not completely required, but if it helps you visualize the chain rule, it's not a bad idea. This function can also be expressed as 3 secant theta to the power 2. In this format, inner function is secant theta, outer function is the power 2 function, and through the constant multiple rule, when we differentiate this again, 3 just stays right where it is. So that's done, constant multiple rule. Now take the derivative of this function, 2 comes down. New power is 1, chain on a new derivative. Throw in the inner function. This is our third time doing this really today so far. When we throw on the inner function, it goes into 2 positions for this one, secant theta here and secant theta here. So we have one more derivative to take, the derivative of secant theta, then we can move through the rest of this problem. On the next line, this becomes 6 secant theta, that's just simplifying all the way to this line. Now, derivative of secant theta, this is the one that goes secant theta times tangent theta. And that means it still simplifies. F double prime at theta is going to be altogether, combine these bases, 6 secant squared theta times tangent theta. And at that stage, we're not done, but we've done most of the work. We can now finally do f double prime at 0 because we know what the function is for f double prime. So the derivative work is done, just one evaluation to go. Any questions or comments to this stage? Okay, when this comes up, say in an exam setting, for the final exam, we do have to evaluate our trigonometric functions. So we can start by saying f double prime at 0 now is 6 secant squared 0 times tangent 0, but then evaluate these functions. And this one's not too bad to get through. Just for the sake of review, let's do both of the trig functions. Secant at 0 is just 1 over cosine at 0. Cosine at 0 is 1, so this whole thing becomes a 1, which means secant squared is also at 0 is also 1. So we're staring at a 1 right there. Next, tangent 0 evaluates to sine 0 divided by cosine 0. That's just a 0 over a 1, which evaluates to 0 altogether. And that's kind of nice in a way. This is a product of three factors. The third factor, tangent 0, is 0, so the whole thing is 0 altogether. So after all that work, we get 0 as a result. Kind of a weird output there, but 0 is just as good as any other number. This feels like we landed at something that's null. Any last thoughts, folks, on getting through this one? Okay, I guess this one's a good reminder as well that trigonometry can come up. If you need any kind of reminders, say tucked away on the corner of your page of notes for the exam, it'd be good to put down some of that information. See section 3.3 for different things that we wrote down for the review on the trigonometry, and that'll be really helpful. So we're moving on to still more differentiation on example number 8. We want to find the equation of the tangent line to this interesting curve right here at the point 1, 1. This one's tricky because the skill that we're going to practice on this one is implicit differentiation. I believe implicit differentiation came up in, forgot the exact section numbers, it's been a while already. That was section 3.5. It also came up again in section 3.9. So sections 3.5, 3.9. This is a really important skill for calculus and the sciences as well in general. So this is a problem where we should really take our time with this. Let me know if you have any questions as we go to differentiate through this, and we'll do this as carefully as possible. This is one of the trickier ones in my opinion. So we have x squared plus xy plus y squared is 3. We want the equation of the tangent line at the point 1, 1. So what we can do is, we want the equation of the tangent line. It means we're computing d by dx on both sides of the equation and then solving for dy dx. So differentiate with respect to x of x squared plus x times y plus y squared. Differentiate with respect to x, the right-hand side, which is just the constant 3. So the right-hand side is 0. That's the nice portion of this. Now here's the tricky portion. Differentiating x squared is no big deal on this one. Nothing here told us x was a function of some other variable, like t, for example. So derivative there, just a 2x. But when the derivative of y comes up, that's not a 1, that's a dy dx. And here's the logic that is behind all this so far. Y is really a function of x. So anytime we do dy dx, we're really dealing with the f prime of x, or we could just relabel that as y prime altogether. Say, for example, you're differentiating y squared. That's a tricky one, because if y equals f of x, that means y squared is f of x power 2. So if you take d dx of y squared, differentiating that one, you're really differentiating that. That's a chain rule problem. We don't actually know what the f of x function is. We just know that we called it y. So the short answer to this is the derivative of y squared is 2 times y times dy dx, which is really very tricky. But let's review it here in the margin to show how it goes, and then we'll apply it up here on example 8. So differentiate with respect to y squared means you differentiate the outer function first through the chain rule. This becomes 2 times something to a power 1, and then chain on a new derivative. That's pretty much how we formatted all the chain rules today. And back when we did any chain rule in the entire course, then we took whatever the inner function is. It could be called secant x. It could be called f of x. If it's f of x, like in this case, it goes in those remaining positions. So now we have 2 times f of x to power 1, so just 2f of x. But f of x is y, so we can unpack this and call it 2 times y times f of x prime. Well, that's this, f of x prime right here. It's the same as y prime. It's the same as dy dx. So we can say 2y times dy dx. So that's how y squared transforms into this. It's very tricky, especially when we're a little bit rusty on it. It's been a while since we've done implicit differentiation. So we'll be really careful as we go to differentiate this left-hand side with respect to x. And we'll do this again when we're doing a problem, say, more similar to section 3.9. But any questions first with this fast discussion on the right? Okay, let's work out this derivative. On the left-hand side, we can use the sum rule, differentiate term by term. And the first one, it's just 2x. There might be something more, but we'd have to know that there's more going on with the variable x. That's a function of something else, like say t for time. Then we move over, we're going to differentiate x times y. But when you go to differentiate x times y, right there, that's already product rule. So let's work out that product rule just in the same way that we've always done it. I'll differentiate the first factor. We'll get a 1 times, copy the second factor, just y. Then we go plus, copy the first factor, x. And now next, differentiate the second factor, y. Well, you could write that in as a y prime. I probably wouldn't call it f prime at x unless you labeled y equals f of x. So either call it dy dx or y prime. So the derivative of y is not a 1, becomes a dy dx out of that. So that's the first term down. Second term, we've done it on the right margin, but let's suppose that we didn't do any of that review work to the right. The way we would typically do this one is visualize it as a chain rule. Y is the inner function. The outer function is 2, so this becomes plus 2 times y to power 1, really, multiplied by the derivative of the inner function. That's y itself. So we'd say times dy dx. And so now dy dx appears in 2 places. Derivative of the left-hand side is done, and the derivative of the constant, 3, goes to 0. So almost there. We now have dy dx in 2 spots. If we want the equation to the tangent line, we need the slope, which means we need to solve for dy dx next. Well, this is really the hard steps getting right to here. And as far as partial credit grading would go, if this was, say, a 6-point problem, I'd probably give 4 of those 6 points just to this step, because this is the major work getting through implicit differentiation, and everything else is not as important as, I would say, this skill right here. Well, any questions whatsoever getting to that equation so far? Okay, now that we're here, there's a couple of ways you could solve this. One school of thought is, we want the equation of the tangent line at 1, 1. We're literally saying x is 1, y is 1. So you can plug those in for the x's, the y's right away if you wanted to. Or you could just solve for dy dx. I think that's how we usually did that in section 3.5. So I'll take that approach this time. And solving for dy dx, First thing I'd want to do is subtract 2x, subtract y from both sides of the equation. So we have 0 equals negative 2x minus y. Next thing to do is factor out to a dy dx from the two terms on the right. That'd be leaving an x plus 2y multiplying dy dx. And I don't know why I said 0 equals. Sorry about that. It would just turn into this. X plus 2y dy dx equals a negative 2x minus y. Let me bring that closer so it's less weird looking. Okay, so factored out, subtracted 2y and 2x and y from both sides. Now divide by x plus 2y, and we have dy dx is equal to negative 2x minus y over x plus 2y. Now this is the slope at any point whatsoever of this curve here. We want to know the slope at one point specifically, 1, 1. And so we say take dy dx. We're transforming this into one specific slope by evaluating it when x is 1, y equals 1, coming from the original information on the point we're interested in. This will take us to negative 2 times 1 minus 1 over 1 plus 2 times 1. So that's the evaluation for 1 for x, 1 for y. And we're almost getting through this one. This is definitely turning into a longer one, I would say. Numerator looks like it's just a negative 3 altogether. Denominator is a positive 3. So the slope is altogether negative 1. So we've got the slope. We want the full-on equation of the tangent line, so still more work to do on this one. But as far as partial credit goes, if this was, say, 6-point problem, 6 points just for a generic idea of the allocation of points, I would say getting that exact slope ought to be 5 out of 6 points. Last thing to do, put it all together. Take y minus y1 is a slope m times x minus x1. We have the specific slope we want. We have the point of the equation we're interested in, so we'll still drop in a 1 and a 1 for the x1, y1 this time. Tangent line equation now goes y minus 1 is negative 1 times x minus 1. So y minus 1 is now negative x plus 1. And let's scroll just a little bit more. We're nearly there. Add 1 to both sides. Y equals negative x plus 2. So that's our full tour of the implicit differentiation technique and getting the equation of the tangent line all in one for this problem. So it was still a differentiation problem, just a lot more going on because of implicit differentiation. Any last thoughts or questions on running through this full problem, start to finish? Okay, well, let's take a look into the next problem. Like we mentioned, we don't have a lot of time. We're at about an hour, 10 minutes. So I want to skip around to the next problems that seem like they're going to be most useful for the review of the exam. Let's skip across example 8, or excuse me, that would be example 9. And I would say this would be a nice, good next set of problems to take a look into. We have x squared plus y squared equals 25. dy dt is 2. So y is a function of t. We can write y is some function of not x, like in the last problem, a new variable t, because the derivative of y with respect to t comes out as 2. We're also told that dx dt, well, we want to find dx dt, but that's a sensible derivative that can be computed. This means x is not just a variable, it's also a function as well, x equals g at t. This becomes a section 3.9 type of a problem. We did one of these on an exam. I believe this would have been exam number 3. I'm already starting to get a little foggy. The exam 3 solutions are available on the Canvas webpage if you want to take a look at that problem. So we want to find dx dt, specifically when y takes a value of -1, x is 2 root 6, and we have a known rate of change for y, dy dt is 2. So that's a lot of information, but all we're really doing is, just like before, implicit differentiation. But this time, we're taking a new derivative, d dt. So here's our next look at implicit differentiation. If we want to find dx dt, that means we take the given equation, calculate d dt of the entire left-hand side, x squared plus y squared. Same derivative, d dt of the right-hand side, 25, where that's a constant, so it'll go to 0. But this time, if we said d by dx, sure, that would have been just a 2x, just like in the prior problem. But if we're solving for dx dt, that's not the derivative we need to take. We're taking d dt, and now this goes a little bit differently. So let's work through this problem carefully, just like before. When we differentiate here, it's done implicitly. We don't know the function g at t. So we think of the power 2 as being an outer exponent. In the chain rule, that 2 comes down. The new power on x becomes a 1 altogether, but we have to chain on a new derivative, dx dt. So that's where dx dt comes from, and that's our goal, to find the value of dx dt. Then we do it all over again. We're taking the derivative of y with respect to t. Y is a function of t, so it's a sensible thing to do. Same idea, 2 comes down as an exponent. New power on y is 1, but y is the inner function, so we must multiply by the derivative of y with respect to t. So here's where dy dt pops out. We know that dy dt is 2 altogether. We also have values for y and x, those particular numbers. This whole thing is set equal to 0. We want to solve for dx dt. So at this stage, we could solve for dx dt. I think in section 3.9, we often made a substitution right here for all the known values. So we'll copy that approach as well. But like we mentioned before, this is the tough step, just getting right to here. We did a lot of different kind of scenarios in 3.9, looking at people walking from a common point, some things with geometry, some work with mechanical engines, and so on. But any questions on getting down to just this equation? Okay, so the visual on this one is we're on a circle with radius 5 coming from that equation. A y coordinate is changing. Its dy dt is 2, which means it's moving up because it's positive. X and y are at these specific points on the unit circle. And now if we substitute in all that information, we'll find out how fast x is moving and in what direction when all this other information here in yellow and in green holds. So let's put in all of our values. We get 2 times 2 root 6 for the variable x. dx dt is the thing to solve for, so we can't do anything with that at the moment. But then go 2 times y. Y is at coordinates -1. And we have a rate of change for dy dt that's at 2 altogether. So the whole thing is set to 0. And now it's a pretty fast equation to solve. It's linear in the variable dx dt. So we have 4 root 6 dx dt minus 4 is 0. So we can say 4 root 6 dx dt is 4. And finally, dx dt, divide 4 by 4 root 6. We get to 1 over root 6, and our work is done right at that step. This gives us more information about the problem. It tells us x is moving to the right at precisely that speed at the only one instant of time when all this information holds here. Well, that's the rundown, second look at implicit differentiation. Any questions whatsoever getting through this one? Okay, well, again, this is a good technique to practice, brush up on before the final exam. It's one that always feels a little bit tricky, but the more and more you practice it, see how it goes, it just becomes one of those things where you're just training your eyes to see how we got a dx/dt, what context that really comes out. And it's really all about the Leibniz notation. It's telling you what you're differentiating with respect to. So putting a dx/dt in front, or say sometimes a d dx in front in a different context, really helps our mind see which way we're really going, and why the results look some way like a 2x, and some other way like a 2x times dx dt. It's all about what derivative you're really taking in the first place. But let's change gears. I think the next problem is a great review one as well. Here we're linearizing something and taking its differential, all in one big problem. So for the first portion, let's also say where this is a good section to review. This is all from section 3.10, right before the hyperbolic functions. If we're going to linearize the function f at a value, a is 0, a good thing to remind yourself is all you're doing is a tangent line equation. There's a formula for this to make it as streamlined as possible. So if you like, you can mention the formula. It goes, the linearization at x of the function f of x is going to be f at a plus the slope f prime at a times x minus the first coordinate, which is just a. A is given to be 0, so we already know what goes both here and here. So if we work all the rest of this out, we can say f at a is just f at 0, plugging in the a value here. Go to the function, evaluate it at 0. This is e to the power 2 times 0, which is e to the power 0, which is 1. So we're pretty much a third of the way done. I guess 2/3 of the way done. All we need is f prime. Hang on, that shouldn't be at x. Let's fix that formula there. Don't know how x creeped in. Let's put in a bold color. All we need to do now is find f prime at a, not x. If it's linear, x should only appear in one spot, right there, specifically. So next step, we take the derivative of this function f. So f of x is e to the 2x, which means always be skeptical when you take a derivative on a final exam, because the chain rule is one of those rules that it seems to crop up a lot. Right after we covered it in that section 3.4, the chain rule was just everywhere at that point, after that point. And this one is absolutely a bona fide chain rule problem. We would break this up as an outer function, e to the x, but it has an inner function, 2x, put in. So that means the derivative would be e to the power of something, chain on the derivative of that something, whatever it happens to be. The inner function, no matter how bad or how simple it is, we can put it in those two spots. 2x here, 2x here, then differentiate that 2x. It just produces a 2, and our work is done. That tells us f prime at x is going to be, I'll put the 2 out to the left since that's the typical way we would write it, 2 to the power of e to the 2x. Said that in a weird way, 2 times e to the power of 2x altogether. So there's our derivative, f prime at x. Once we have that, we can calculate f prime at a. So we're looking at that part of the formula, which means we're doing f prime at 0 which means we have to go to our derivative already calculated. That's the slope at any value x, but at 0, it becomes 2 times e to the power 2 times 0. That means it's just a 2. Since e to the power of 0 we get again, it's still just a 1. Then we just put it all together. We can say, by the work above, linearization at x is f of a, let's look that up, it's a 1, plus the derivative of f at a, we found that to be a 2, times x minus a is 0. And we made a comment about this when we did it in section 3.10. If you left it in that form, that's kind of weird in a certain sense, because it's not fully simplified. You're taking x minus 0, that's really just 2 times x. But if you did leave it in that form, I wouldn't take off credit because it conveys the information of the function value, the derivative, and the point you linearized was a is 0 if you left it in that format. So it actually gives you some pretty good information in that form. So it's an acceptable answer at that stage, but if you really wanted to, you could write it as 1 plus 2x, no harm there. If it looks like a lot of algebra, not a bad idea to just skip to the next problem. But that's how linearizations go. We should be prepared for doing one of those on the real final. Any questions about getting through this one? Okay, well, as far as the other ones are going to go, part B rather, it's asking for a differential. And this one we have to be really, really careful of. I think on a real exam, when I ask for a differential, I think I actually put this in bold. Just to give an extra hint, I'm not asking for the derivative, although the derivative is a part of it. When it says differential, there are certain expectations that have to be met to get a full credit on this answer. So let's write down a quick formula. This is really the major tool that we required to get through section 5.5, the substitution rule. When we say differential, it means if y is a function of x, then dy equals f prime of x dx is the differential. Differentials have lots of uses in calculus 1, calculus 2, calculus 3, and beyond, vector calculus, and so on. But for the moment, for our purposes, when it just says compute the differential or what is the differential, you must have a dy there, you must have a dx there. If the derivative involves more than one term, you need parentheses around it because dx is an ordinary variable in algebraic structure. So we have to write this in the correct algebraic form. Well, we already have the derivative f prime of x. It's right here. We're linearizing the same function, this f of x here. So when I ask for a differential in this question, really all we had to say is, on one hand, it's not too bad of a problem, but I think the instructions on the exam would have to be a little bit more specific. Let me put in a quick edit on this one. Sorry for the edit here. What is the differential of f? Let me just rewrite. Find the differential for y equals f of x, which is equal to the e power 2x. I think actually let's write it in this form. Y equals e to the power 2x. So sorry for the quick edit. On the real final exam, I think I wrote it with instructions a little bit more specific because the problem with just saying f of x is this and find the differential, we could have labeled e to the 2x as being w if we really wanted to, and then it would have started with a dw. So I need to be specific with what the variable is on the far left to really ask that kind of question. And I made sure to do that on the real exam. So sorry for the edit for the sake of the notes here. For this problem here, with the revision here in red, we would start off by saying dy equals, take the derivative of e to the power 2x, which we've done here once already painstakingly. It's 2 times e to the power 2x. And then since the variable is x on this one, we just put on a dx. And that's the full and complete answer. We just have to remind ourselves we must separate the dy dx in this kind of way, and they must both be present. Well, that's linearization and differentials all in one as a two-part problem with a revision. Any questions or comments on this one here? Okay, and again, because we're running short of time, I want to kind of cherry pick some of these problems to look into the trickier ones, the bigger concepts. So I want to say skip through maybe this problem right here. I feel like this one is a big challenging problem. Example number 16 in particular, because this is the optimization type of problem. This is the kind of problems that we saw in section 4.7. This one's tricky in the homework. It was tricky on exam number 3 as well, getting through section 4.7. And what made it tricky was to get full credit on these kind of problems. Let's put this here down as a comment as well for the sake of the review. We must show all steps using the first or second derivative test. So there's more to this beyond just finding the critical number. Getting a critical number doesn't prove that there's a minimum or a maximum of the function. We saw plenty of examples where that happened. There's a critical number, but no local min, no local max, no absolute min, no absolute maximum either, no extreme values. So we have to actually use these tests, one or the other. It's up to us to pick the test to prove we really have an absolute maximum or an absolute minimum. So that's the easy thing that was the easy thing to miss on the homework and the exam, making this one a very good review question. You can expect a problem like this one on the real final exam as well. Different entire context, but same amount of complexity. I think it's a little bit easier on the real final because this one is also involving a trig function, which makes this work a little bit harder, it seems like, when trig comes up. But here's the context. It says the range of an artillery shell, so imagine the army working on this one, fired at an angle theta measured in degrees with the horizontal is that. That's going to be the range of an artillery shell fired out of a howitzer or some kind of big cannon like that. V naught is the muzzle velocity of the shell in feet per second. So we have V naught squared there. But if that's the case, we're going to make a big assumption and assume V naught is constant. So the gun is going to be operating in a normal way. The muzzle velocity of the shell isn't going to change from operation to operation. That would make the gun pretty much useless for precision shelling. So we have muzzle velocity as a constant here, squared. G is the constant acceleration due to gravity. It's kind of nice. It's said it's constant, but let's just say it again here, just to prime our mind to remind ourselves of that. G is constant. So if G is constant, V naught's constant, it means the entire coefficient here for sine, V naught squared over G, is also constant. Now, the thing that varies is going to be the angle theta. So the gun can either move up or down. It'll affect the range because the velocity of the muzzle velocity of the shell is always going to be the same. We want to find the angle of elevation that will give the gun its maximum range. So we're evaluating how far this gun can shoot. And not just that, we want to know specifically what angle. Actually, that's the only thing we want. We could put it in the function to find the range, but it said just find the angle. that's going to lead to the maximum range. If you find the maximum range as second part to the problem, no harm done. But once we get theta proved to be the maximum, we could just stop right at that step. So that's the setup so far. And because we're thinking of something being shot out of a gun, sometimes a visualization really helps with these kind of problems. So let's just draw a really simple diagram. Here's a point here and a little line segment. This is the gun. Doesn't have to be artistic. It's set at a certain angle. Let me just kind of extend it this way. It's set at a certain angle theta. It fires and the shell comes out. Gravity takes over and it brings it back down to Earth. So that's the rough visual on this one. But what's helpful with this kind of diagram is if we're going to maximize a function R, it's a good idea to have a reasonable idea of what is the domain of that function. As the domain will be all the plausible values that we could really use for theta. And we can say by this diagram already, theta should probably be bigger than 0 radians, or 0 degrees if you prefer, because if it's set right at the horizontal and you fire that thing, that could be catastrophic for the gun, probably deadly for people operating it. That's going to be a really loud, catastrophic explosion. So you should tilt that thing up a little bit, hopefully more than just a little bit. But at the same time, we don't want to fire it straight up into the air either. So we would say that this should be less than 90 degrees, or pi/2 radians would be the typical unit we would use. And that's a reasonable domain for this kind of function. Between 0 and pi/2 is the domain of R. Knowing that domain is going to simplify a lot of the steps that we are going to have to take when we do the optimization. And now, first thing, whether we're using first or second derivative test on this, first thing is just to differentiate R. So we're on to that next step. But any questions with the preliminary analysis, in particular getting the domain? Okay, well, let's start by differentiating this on our next step. You could call this R prime, or dr d theta wouldn't be a bad approach. We're emphasizing that the actual variable is theta itself. So I'll go in Leibniz notation, dr d theta. Next step is, there's a good old constant multiple rule here. V naught squared divided by g just stays right where it is. After that, we differentiate sine at 2 theta. That's really a chain rule problem, so let's be careful with this one. Inner function's 2 theta. Outer function sine. When you get a really good handle on chain rule, sometimes this is how people compute. Take the derivative of sine, this would become cosine at 2 theta. Then we multiply by the derivative of 2 theta, but we already know that's a 2, so let's just go times 2 right here and now, just like that. So that's dr d theta. Any questions with getting that first derivative down? Okay, we can simplify this a little bit more by just moving all the constants off to the left. This is also altogether twice v naught squared divided by g is multiplying cosine 2 theta. And what we're really going for after we find the derivative, here it is the critical number, which means we set it to 0 and solve. So we want to know, when is cosine 2 theta times a constant equal to 0? That's not too bad of a problem. In a trigonometry course, there's a lot of work in finding all solutions to cosine 2 theta equals 0. But keep in mind, we have a really restricted domain. We could revisualize the domain kind of like this if we'd like. Here's the unit circle. We're going from 0 to pi/2. Those are the only plausible values. we plug in 0, well, that's out of domain. But if we did plug in 0, that would have been cosine 0, which is a 1. If we plug in pi over 2, that's also out of domain. Cosine 2 pi over 2 would become cosine pi. That would be -1. So that's not going to hit us with a 0 either. So there's some value between 0 and pi over 2 that's going to land cosine theta right at 0. And this is the angle that would do the job. Pi over 4. We do know that cosine at pi over 4 is root 2 over 2. But this is cosine of 2 times pi over 4 from the factor of 2 inside the function here. That turns into cosine pi over 2. And cosine of pi over 2 is the x-coordinate right here at the unit circle. It's exactly 0. That means our search is done for the critical number. The only value between 0 and pi over 2 that's going to make all of this come out 0 is when you plug in a pi over 4 right there for theta. Then you get cosine pi over 2, which is 0, wipes out that constant here on the left, and that's our critical number. So let's say here to summarize, this implies theta equals pi over 2 is the critical number. So now that we have the critical number, our job isn't done. We have to prove that there's nothing weird going on with this model. Maybe there's another critical number, for example, that we haven't analyzed, or maybe the model's completely wrong and we have an absolute minimum, not a maximum. We need to prove going further with first or second derivative test that at the critical number, we get the maximum range. Seems kind of plausible, right? Pi over 4 is 45 degrees, so seems like if you aim something that's shooting a projectile at 45 degrees, that should do the job, but we have to now prove that that's the case given the original model here. Ashton said, wouldn't theta be pi over 4? Instead, as it is, multiplying to get pi over 2. Oh yeah, thanks for spotting that. I had the pi over 4 here. Don't know what went wrong on that step right there. Thanks for your careful analysis on that one. I think I was focusing on that last equation too much. And that's another good reason on why we have to be really careful that we prove that we have the right value through the first or second derivative test. It's not pi over 2 at all. Again, that's if the gun is aimed straight up. Let's revise this back to pi over 4. So that pi over 4 was the theta that you plug in to get the 0. Again, thanks for spotting that error right there. Does that make sense to folks with the correction? Okay, we have a revised critical number, and now there's a couple approaches you can take. I'd say first derivative test would probably work just fine on this one. Let's give it a go and see how it works. For the first derivative test, I need to find out the sign of the derivative, dr d theta, on 2 different intervals. The interval between 0 and pi over 4, and the next interval between pi over 4 and pi over 2. When we did this in class, we usually organize in a number line, so let's copy that approach. This time, my number line looks a little bit more like this. Open circle here for 0, and pi over 2. I'm putting open circles there just to remind me that those are not in the domain whatsoever. What pi over 4 is, here's our critical number, and between 0, excluding it, and pi over 4, excluding both of those, we will analyze dr d theta, and same for this interval. When we did this kind of problem, whether it was in section 4.7 or even in section 4.3 when we were getting started, the next step was to use test numbers or test values, however you'd like to call it. The critical numbers can't be used. 0 and pi over 2 cannot be used. They're not even in domain. So I'd say probably the nicest test number to use might be something right here. What would be a good value right there? We're dealing with cosine, so maybe pi over 6 isn't a bad choice. Take theta equals pi over 6. Then dr, d theta, evaluated when theta is pi over 6, would be equal to, we're plugging pi over 6 here, so this is 2 v naught squared over g, cosine of 2 times pi over 6, which would give us cosine pi over 3, 2 v naught squared g cosine pi over 3. Cosine of pi over 3 is exactly 1/2. So this is 2 v naught squared over g times 1/2. It's a big amalgamation of constants, but g, the acceleration due to gravity, this is positive. V naught squared is positive as well. So the whole quantity right here is a positive coefficient. That means the first derivative is positive here. And that means the function r, the range of the shell as it's fired, is increasing as the angle lifts higher and higher and higher. That kind of fits our expectations of how we expect physics to work. But there's probably some diminishing returns here. And after we go beyond a certain point, we're going to lose some range. It's going to be aimed too high. It won't get too far. But we need to prove that to show the derivative is negative here. Pick another convenient value. So that's our first test value. We got positive. Now we're hoping for negative on the next one. So pick any number that's convenient. And no harm done if you said just pick something like, well, pi over 4, between pi over 4, pi over 2. If you get just a decimal number, put it inside here in the calculator. That'd be a fine route to go as well. I'll pick a number that's easy to calculate for cosine at 2 theta. Between pi over 4, pi over 2, we could use, say, pi over 3. That's in domain. So let theta equal pi over 3. Then dr d theta, when theta equals pi over 3, is, go up to the derivative again, 2v naught squared over g, that's a positive constant, cosine. We're plugging pi over 3 here, but also doubling it, so now it's at 2 pi over 3. 2 pi over 3 is right over here. We take a cosine value at 2 pi over 3, we end up down there, negative 1/2 on the x-axis. So this is now 2v naught squared over g times negative 1/2. That's absolutely negative, positive number times a negative number right here. That tells us dr d theta is less than 0. We aim the gun too high, beyond pi over 4, 45 degrees, up to pi over 2, but not at pi over 2. That sounds suicidal. It's probably going to come right back down. But in that range, it's always negative, which means range is decreasing. So this shows we have it increasing, turning over to decreasing. There's only one critical number. And that's what finally tells us and proves to us there is an absolute maximum that we can have for range at angle of elevation, the critical number pi over 4 specifically. So we're just about there. We just need to state our conclusion. At elevation, theta equals pi over 4, range will have an absolute maximum. You could say by the first derivative test or the second derivative test if you used it. But if you didn't say it on this final exam, I'll know which test you used. That would be fine to end it just right here. Well, that's the full analysis on this one. Kind of a fun problem because it's kind of easy to visualize what's going on with this sort of diagram. There's really more to this. There's weird things that go on with physics. There might be more issues with, say, just the drag of air on the shell itself if we bring more and more to this kind of picture. Well, if we simplify the model way down to just that, our conclusion is 45 degrees. Well, any last thoughts or questions at all, folks? Getting through this optimization problem here? Okay. Well, as far as doing these on the final exam, I'm not going to give a really long problem. Kind of like on exam 3, I'm going to try to keep the optimization problem kind of short and sweet that you can run through and not get too bogged down. Even though it's a 2-hour exam, it would not be the funnest thing to spend 40 minutes on one single problem. So it'll be pretty quick. Take a look at the ones we've done in lecture, the ones you did in homework in section 4.7. Take another look at the one you did on exam 3 or this one right here. And that will give you a really good idea of what to expect on the real final exam. I'm not going to write down some totally bizarre new scenario that would take too long. They'll be kind of short and sweet. And this one is a little bit more on the longer side, I would say. Well, let's move on to, at this point, with our remaining time, this was a really important problem for us to definitely take a look into. But I think the next one we should take a look into ought to be the integration problems. I put a note on some of them, not all problems we got to in this course, so some of these problems are excluded, like this one here using Newton's method. But for the sake of making sure we get to these problems, let's take a look at example number 20 next. I had it all compact in these 9 different parts. I felt like you watching me separate them all out was the best use of class time. So I have parts A through I all separated out here. Let's try solving as many of these as we have with the time we have. If you have a little bit of extra time, or if there's any other problem you'd like to see solved, don't hesitate to ask. I'm very happy with changing gears. So here's the last portion we'll do for the review, getting through integration. For this last block of problems, we're looking into sections 5.3, 5.4, 5.5. And like I mentioned at the start of class, this is the kind of content that Calculus 2, if you're taking it next semester, really launches into, hitting the ground running starting in chapter 7, section 7.1. So this is a good set of problems to review just for the final exam, as well as before starting Calculus 2. To begin with, on this one right here, we're looking into a definite integral. The answer is going to be the signed area under the curve for this entire function, the integrand. And all we really have to do is come up with an antiderivative of that, evaluate it from the lower limit of integration to the upper limit of integration. So now, here in finding the antiderivative, I guess that's also section 4.9 is where we started talking about antiderivatives. We need to find the function that you would differentiate to get 5e to the x. Antiderivative of that is automatically just 5e to the x, because the derivative of 5e to the x is 5e to the x. That sounds redundant to say it that many times, but that's your mental check each time you do a value right here, term by term. Differentiate this, see if you get the same term in the integrand. Then we just do it all over again. We have 3 sine x there, so we have to ask ourselves and answer the question, the derivative of what in that position will give us a sine? Well, it's tricky in a certain sense because the derivative with respect to x of cosine is not a positive, it's a negative sign. So to make this come out just right, we have to flip the sign on this one. Go -3 cosine x. And the check here is the derivative of cosine x is negative sine x. The extra negative multiplies the -3, flips it back to positive. And so that's one critical area of the section 3.3, trigonometric derivatives, to watch out for. Those negative signs, they're easy to lose track when you're going backwards doing antiderivatives. But once we have it all, we take this entire antiderivative, evaluate it from the numbers 0 to pi. Any questions to this stage, obtaining the antiderivative itself? Okay, there's a definite order it always has to go in. It's always the upper limit plugged in first through the fundamental theorem part 2. So take pi, plug it in for x to get 5, e to the power 5 minus 3 cosine pi. Then go minus, do it again, plug in 0 for x, the lower limit of integration. So always in that specific order. This would give us 5 e to the power 0 minus 3 times cosine 0. And another reminder for the sake of the final exam, this was an expectation on homework assignments as well. Whenever something like this comes up, cosine pi, we must evaluate all trig functions at common angles. By common angles, we mean like pi, 0, pi over 2, pi over 6, 5 pi over 6, and so on. If this was just cosine 3, that's a pretty awkward angle, and it's appropriate to just leave it in that format. But if we can simplify it, because cosine pi is a nice rational number, it's -1, we should always do those evaluations, just like in a trigonometry class. So it keeps on going. We have to simplify from here. This is worth most of the credit because anything beyond this is just trigonometry and arithmetic. So if you get to that line, I give almost all the partial credit, essentially one last point for simplifying it down. So it's 5 e to the pi. This is -3 times cosine pi, which is -1, so +3, minus e to the power of 0 has come up a lot already today. That's just 1, so it's 5 times 1 for a 5. Cosine 0 is 1, so this is just -3. So this is 5 times e to the power pi, then 3 minus, plus 3, rather, minus, that's a positive 2, so it's 3 minus 2. 5 e to the power pi plus 1 is a good stopping point. You could put it in the calculator at this stage if you wanted to, but this is where you'd be expected to end, where most people ended on the homework as well. Write down the exact answer in simplified form. So that's our first one down. We'll practice all the remaining ones. Let's see if we can get through the list. But any last thoughts or comments on getting through this one? Okay, looks like the next one's a definite integral to take a look into. Good amount going on with this one. 1 over 2x, e to the power -2x going on here. So, we've dealt with e to the power positive 2x. So here's another thought on just preparing for this one. We know that the derivative with respect to x of e power -2x would be, give it a little bit of space, e power -2x. Then the chain rule says you differentiate -2x and multiply. That would just put a -2 right out in front like that. So that's the whole derivative of this function here. If you can differentiate it really quickly in this kind of way, and it's not too involved, you might be able to give a fast antiderivative as well. This means the antiderivative of e power -2x dx would look like this. Go e power -2x. That's not the entire story, because we know if we differentiate it, it gets multiplied by a -2. If there is no -2 here, we just divide by -2, and that gives us an antiderivative. Then, just to make the formula concrete, we can add the arbitrary constant of integration, and that's the formula for this one. It's a good idea to think in these kinds of terms whenever you can, because it's a big time-saving step. It prevents us from having to use the substitution rule, section 5.5, but we'll definitely use it on, say, part C down below. We'll review it very soon. So let's start off this integral after looking into just the scratch work here on the right. I would reformat the integrand in one other way and rewrite this as 1/2 times 1 over x minus e to the power -2x dx. That's a kind of bizarre looking simplification, but if you've already known why we did that, good on you. This is the next really critical formula that's easy to forget. If you want the antiderivative of a 1 over x dx, you cannot use the power rule in reverse for this one. This one's the natural log of the absolute value of x plus a constant. So leaving it in that format, separating out to the 1/2, primes our mind to recognizing the right antiderivative on the 1 over x. After that, we're ready to start. We'll go left to right. Constant multiple rule works in reverse for antiderivatives. We just put in 1/2. Antiderivative of 1 over x is natural log absolute value of x. We just need an antiderivative. The simplest one will do, so we're not putting in the constants here whatsoever. So simplest antiderivative is just natural log x. On this one, it goes negative e to the power of negative 2x. This should be positive e to the power of negative 2x. Divide by 2. Now, that looks weird because we had a negative sign here already. But here's the thought. If you differentiate all this, derivative of e to the power of negative 2x is a negative 2 e to the power of negative 2x, which means a negative 2 comes in front, 2 over 2 cancels, and we keep that negative sign right where it is. So if you can differentiate that and get the prior answer right above and the right sign, you're home free on that one. That's the right and complete antiderivative on that term there. Then we take all of this, evaluate from 1 to 3. We just need to show the evaluation, simplify, and we're home free on this one. Any questions whatsoever getting through the antiderivative on this one? Okay, well, final step, just evaluate. We're going to plug 3 here. Absolute value of 3 is just 3, so we can just write it more simply as natural log 3 at this step. If that was a negative 3 for any reason, then the absolute values are required to give us the correct answer. So we're just being careful mentioning them here. Plus e to the power of negative 2 times negative 3 over 2. They'll go minus. We're plugging in 1 now. 1/2 times natural log of absolute value 1 is just a 1. Plus e to the power of negative 2 times 1 over 2. So that's all of it together. This one's term is kind of nice. Natural log 1 is 0. So that whole term inside that group cancels right off. And not too much to simplify on this one. It's now 1/2 natural log 3 plus e power 6 here over 2. Then distribute all the way here, that negative sign, it's e power negative 2 over 2. And I probably wouldn't do much with this one at this stage. I think it's in a pretty decent simplified form. It has a least common denominator, so a equally correct equivalent answer might be natural log 3 plus e power 6 minus e power negative 2 over 2. But you really just change the algebraic form. No terms canceled, nothing combined. So either way you express it is just fine. You can save a lot of steps. You don't have to put this in the calculator. I'm looking mainly for the exact answer. Well, we got through that one. Looks like they get trickier as we go in parts C and D. But any last thoughts or questions on part B? Okay, now for part C, here's where we really just can't avoid, unless we've done loads and loads of these, dozens and dozens and dozens of these kind of problems. This is a problem where I would not avoid using the full methods of section 5.5, the substitution rule. So let's show that process completely. Start reviewing section 5.5 in earnest, starting with part C. It looks like part D is another one of those same kind of problems. So section 5.5, the whole goal is use differentials to reverse the process of a chain rule. And if you're thinking of chain rule, that means there's got to be an inner function. On this one, the inner function that we see is x squared minus 1. We mentioned before, there's no guarantee that picking this as u is going to work out. So sometimes we have to get a little bit creative and inventive. But often it's a good start, particularly from the problems that we did in the homework, the problems we did in the lecture as well. Look for a function going inside some other function. So there's an inner function there. The outer function is the square rooting function. We'll set u as x squared minus 1. Once we have u, the very next step we take is take the differential. We label it as u, the next line should say du. Then we take the derivative of whatever the function is as labeled. This derivative is fast, it's just a 2x. But then we have to multiply by dx to make it a complete differential. And this is called the substitution method because that's really, quite literally, all we're doing, a whole bunch of substitutions. We look at our format of the differential, it does involve an x and a dx. The only thing that's extraneous is that 2 there, but we can rearrange and divide by 2. Call this 1/2 du equals x dx. And the x dx we see in this integral here, we're just going to replace with the 1/2 du. X squared minus 1 we see here, that's going to be replaced with nothing but u itself from the original substitution. And this is the initial setup for using this method. Any questions on getting through it to this step here? Okay, well, loads of mathematics is just making substitutions that are sensible. And so always just think in terms of that. Go back here, start making swaps. I'll go equals, give it a little bit of space, then the integral sign. First swap, we can say we have a u to power 1/2 coming from right here. X squared minus 1 is what we called u, and I just changed the format of the square root to its actual exponent, power 1/2. And next step is the entirety of x dx, whether they're separated or brought together, is just a 1/2 du. I'll place the 1/2 right here. Du, in the normal spot, we would place it on the integral, the far right. And that's all portions now substituted out. The original integral is a mystery. It's not the antiderivative of the first thing times the antiderivative of the second thing. The antiderivative of this is tricky enough in its own right. But once we do the u substitution, that's just now an ordinary section 5.3 integral that we can solve. So we're on our way. On the next step, keep the constant 1/2 right here. Include a lot of extra space. Put down the base u. In the antiderivative, it goes up by 1, so we're adding 2/2 to get 3/2. We divide by that new exponent, so multiply by the reciprocal, 2/3. And then finally, it's an indefinite integral, so this one must be the most general antiderivative. We must have the constant of integration here. It's worth 1 point. If you forgot it on all antiderivatives on the exam, I'd only take off points 1 point once. I'm not going to nickel and dime you every single time, but it is important, so don't forget to put that portion here, the plus c. It's still not done. For 1 more point, we have to undo the substitution u and write it back in as x squared minus 1. So the final step is, this is 1/3 after canceling. To power 3/2, we have x squared minus 1 plus the constant of integration c. And that's our entire answer. If you have extra time on the final exam, it's not a bad idea to go into the right part of the margin, differentiate whatever your answer was, and show that you would really get to this. It involves the chain rule, but everything comes out just the way you would expect. Well, we did it, folks. That's our first, for the review here, run through a section 5.5 problem. Any thoughts or comments on getting through this one? Okay, and maybe one more comment we should duplicate that we mentioned quite a lot. We don't always do U substitution because, as you can see, it's a process. There's lots of writing to get through it. We only use U substitution when it's not obvious at all what this antiderivative is going to come out as. When I look at that problem, x times square root x squared minus 1, I can't predict it's going to come out to exactly that format. I haven't done hundreds of them to know that that's what I'm expecting to get. But when it comes to these right here, e to the power negative 2x, these are not as bad. If you can predict that you just have to divide by 2, the sign comes out right when you differentiate, it's always a good idea to try to streamline it in this kind of format. You could have used the substitution rule right here, but it kind of makes a mountain out of an anthill. And these are the kind of problems in a Calculus 2 setting where the substitution rule really is skipped. The author will say, we do a mental U substitution and just arrive at this answer. So that's a common thing that's done in the next course. But for plenty of problems, it's something no one would avoid, like in part C and definitely in part D we'll solve next. So here's our next U substitution type problem. It's not obvious what the antiderivative should be for something that looks like that. But like before, we have a tangent function with a function on the inside of it, 1 over x squared. So that's a strong suggestion to make that be the u in the U substitution. We'll copy the process just like we did in part C, pretty much verbatim, just with a new integrand. Start off with whatever your u is. It's 1 over x. I want to reformat that as x power negative 1, just to streamline the derivative. In other words, you never want to take the derivative of 1 over x with the quotient rule. That's taking loads and loads of steps when derivative of that is just negative x power negative 2. Never use a quotient rule on these kind of things. Not that you'll lose any credit, it'll just save you time not using the quotient rule. Now next, du is going to be equal to, take the derivative of this, we'll get negative x. In differentiating, the power goes down, so negative 2. And honestly, that's easy to forget now that we've been doing antiderivatives. So always think down for differentiation. That'll help out. This is the entire differential now. And with what we see here, not quite in this format. You know, there's an extraneous 3 that occurs here. But we can clean this up. And if we don't like that 3, the constant multiple rule for integration says you can just pull it out. Write it as tangent 1 over x squared dx. So now that weird 3 is no longer a problem. Other issue is there's no negative sign here, but we could just move the negative sign to the opposite side. Multiply both sides of that equation by negative 1. And negative du is now positive x power negative 2, or you could rewrite that as 1 over x squared dx. And you can separate this out as tangent of 1 over x times a 1 over x squared, or it's not a bad idea to just visualize it this way. X squared in the denominator is really just that 1 over x squared. dx is there. We're going to replace all of that in blue with a negative du. So now finally, this is all together 1/3. Give it a little bit of space before writing that 1/3 in the integral sign. Tangent u and then we have x squared dx down in the denominator. So for our x squared dx, we're replacing with a negative du. So du is going to go here. Negative sign goes here. And you know, this one is kind of a tricky question at this stage. Antiderivative of tangent u. We'll kind of drawing a blank on that one, but any questions or comments to this stage so far? Okay, well, we got pretty far through the problem, but you know, now that I'm looking at this one really closely, This one looks like a pretty tough question. Let me show you the reason I would say that. If you look into section 3.3, this is where our derivatives first came into play for trigonometric functions, and they do double duty as antiderivative formulas. But look at these derivative formulas. If you say, take the derivative of a tangent, you get secant squared. This would mean the antiderivative of secant squared is tangent. But that doesn't tell us that differentiating secant squared gives us tangent whatsoever. If you differentiate secant squared, you get something entirely. So to have a good formula for this, I'm looking for something like, say, a tangent on the right-hand side to get an antiderivative. If we're looking even further, say go to section 4.9, here's where we have a nice table for antiderivatives. But I don't think this is going to save us either on this problem. I think I accidentally put in kind of a beast of a problem on this one. We look into, say, not 4.9, but rather this would have been 5.4 on indefinite integrals. The authors provide a nice table of antiderivatives. Here they are. It's not a bad table to look at, just we made a comment before. Not everything is here, so you want to do a more extensive kind of search if you're using this table. But notice what's missing. It never says at any point what is the antiderivative of a tangent function. We have one for sine, absolutely. Antiderivative of secant squared is tangent. So tangent inverse, that doesn't work. We are talking about tangent itself. This is a good reminder that antiderivatives are kind of tricky. And I just want to emphasize one other thing, that this problem like this one would not be on the final. This one extends more into calculus 2 territory, it's looking like, on accident. Sorry, didn't mean to throw a kind of a nasty one in. But we got to practice U substitution a little bit on this one. So it's not all was lost on it. If we were to try to come up with an antiderivative, let's give that a try to see if we can show what it ought to be. Let's say we differentiate with respect to u, because I have a du here, that's the right value to take. Antiderivative of tangent, a little bit foggy. Let's put in natural log. How about secant u? So if we go with the natural log secant u, let's see what happens when we differentiate this one. It is a chain rule process. Secant u is going to go down to the denominator. That's what happens when we differentiate a natural logarithm. Then we multiply by the derivative of secant u. But here's where a mathematical miracle is going to occur. Derivative of secant u, let me put secant u back down in the denominator first. Now this derivative, which will multiply up into the numerator, derivative of secant u is secant u times tangent u. And that looks almost too miraculous, right? Because secant u cancels off. It gives us a tangent u. That's exactly what we want. We want to say differentiate something and get tangent u out. Differentiating the natural log of secant u, that actually works. That does the job. And we can extend this even further. Turns out the formula doesn't change if you slap it with absolute values at the same exact time. So out of nowhere, this one is a pretty hard one. I'm not going to ask anything along these lines where we have to guess a very random function to come up with an antiderivative. I wouldn't come up with this on my own in an exam setting. I've taught calculus 2, so my memory got jogged when I looked at it. So I made sure that the problems are a little bit more approachable in the real final when U substitution comes up. But just for the sake of finishing it off, because it's not great to have a problem hanging, let's keep on going with a supplied antiderivative. This becomes negative 1/3 natural log absolute value of secant u plus a constant. And we know the derivative of natural log secant u miraculously came out as a tangent u, so we're on the right track with that. Then the last step is to write this as -1/3 natural log absolute value of secant. We make a substitution for u right here. U was x power -1, or just at 1 over x. Let's go with a 1 over x because that was the original notation of how the problem started. And then add a constant. So if you put all this together in this specific way, where the unfair part was this derivative here on the right, then that's the antiderivative in part D. Once again, sorry for the nasty one on this one. Whenever you get to this step, it's always going to be stuff that we've looked into, that we've specifically done in class on an honest final exam question. And when I go to grade the final exam, if anything like that did show up by some random error on my part, I would curve the final exam to make up for it. So you're not going to lose points if something weird like that happened on the final. But we got through it. That's two tricky kind of U substitution problems. A standard one, part C, and a nasty one. This is really one problem that we'd see in the next course in part D. But any last thoughts or comments on getting through any of these so far? Okay, well, we've come up to the last bit of the time. There's some problems here that we didn't finalize completely, but I'll try to get these solved as fast as I can. So if you want to look into the completion of these notes, I'll try to get these available. If there's any questions you want to see done in a faster way, don't hesitate to email me. I'll be happy to email you back, post a solution to it. But last advice for the exam, like we mentioned before, definitely put together your page of notes as soon as possible if you haven't done so already. Another good advice is take a look at your original exam 1, 2, and 3. Look at any problems you might have missed. You can see the comments I left on your exam, or just scroll through the Canvas webpage. And on the Canvas webpage, I have, under every single exam, information block, the actual exam solutions, so you can see the full step-by-step solution to any problem that you missed on exam 1 through 3. That'd be a definitely good idea to take a look of information to take a look into. Complete the solutions to all the homework exercises as well. That'd be the next thing to take a look into to get, really that's doing double duty, getting your homework grade up and practicing the final exam. And then if you have more time to spare, you can take a look into the further questions here or any of the problems we didn't solve in this review here as well. But any last thoughts or questions at all, folks, before we call it a night today? Okay, well, have a great night, everyone. Good luck on the final exam if you haven't taken it so far. I'll try to get those graded as soon as possible. And once again, grading is probably going to extend sometime through the weekend, might conclude sometime on Monday afternoon at the very latest. But take care. Don't hesitate to email if you have any questions, and I'll be happy to help out. Have a great night, folks.